welcome to São Paulo if you're not from here. To say a few things about the school here, about ourselves. So I'm not from the ICTP-SAIFR, I'm from the University of São Paulo, but São Paulo is a large city with many people, and we work with each other a lot, as much as we can. And this school has been going on for quite a while, and we've been able to attract very interesting people here. This year, I'm also one of the organizers, and I'm also giving some lectures, but just the basic ones. Still, you have many of the other speakers which are really world-renowned scientists, and they are here to try to teach you some of the basic tools of cosmology, some of the basic ideas, what's going on, what's new, what's interesting, and to help you actually get a start in working with some problems. You don't necessarily have to be able to work with everything that you're going to see here, but the idea is that you come out of this with some tools, with some skills that you can then use to do something that you like. So my name is, oops, sorry, here. My name is Raul Abramo, here. Sorry, I didn't say my name. So I'm going to teach you the 3 first lectures in large-scale structure. Actually, the first lecture of today is just a very, very broad, basic review of general relativity, some cosmology, some dark matter and dark energy. I understand that most of you already know some of this. It's going to be boring for many of you, but for some of you, maybe not so boring. So if you have some patience, the first lecture is going to be very basic. Then we start to talk about structure formation, which is how the universe goes from a state, initial state of which is very homogeneous, very isotropic, to creating the structures that we see today. Galaxies, of course, inside galaxies, stars, groups of galaxies, clusters of galaxies, all these inhomogeneities that characterize the universe today, and which are one of the, probably the main topic of research in cosmology these days is structure formation and how physics affects structure formation. So dark matter, dark energy, modified gravity, how they affect the formation of structure in the universe. So that will be these lectures, which are shared between myself and Rogério Rosenfeld. Rogério Rosenfeld is not here these first few days, but he will be here Thursday and Friday. What else? The program, you already know what the program is, but let me just show you what it is. So here, in the morning, I'm going to talk to you in the morning these days here. Then Mehrdad Mirbabai is going to talk to you about inflation, which is the theory that tells us how the initial conditions of our universe, and also it solves many of the long-standing problems in cosmology. And then Konrad Dworkin is going to talk to you about cosmology in these lectures here. That's for the first week. The idea is that we also give you some exercises, some problem sets that you can then try to solve here in these discussion sessions and exercise sessions. And we will try to be here to help you a little bit with that. Antonino Troia, which is here, say hello to everybody. He's going to be helping us a lot. And you already met Jandira outside and the staff of the ICTP-SAIFR. If you need anything, if you need T-shirts, or if you need to get your bag or something to store outside, there are lockers that you can ask for. We usually have a lunch break here. There's plenty of places to eat lunch around here. We have 1.5 hours, which is enough to go out and start having some conversations and so on. And so let me just get to know you better. So who here is from Brazil? Please raise your hands. Shoo, lots of people. So who is from South America? Please raise your hands. No, sorry. South America excluding Brazil, so that I know who speaks Spanish and so on. And who is not from South America or Brazil? Okay, all right. So one last thing. I had an accident with my foot, so I can't really stand up too much. I hope tomorrow and the day after I'll be better, but I'll have to be sitting down as much as I can, as per the doctor suggested. So I'm sorry, but I'm going to be very boring here. I'm going to be sitting there and with my foot up. So I'm sorry for that. I usually walk around a lot, and I scream, and I move my hands. And I'll be moving my hands a lot, but not moving around the room a lot. So I'm sorry for that, but I really have to be sitting down here. OK, so the idea is that you ask questions. This is for you to learn skills and to get that information or insight that you couldn't get from the textbooks that you read. So the idea is that you ask questions. And it doesn't matter that if you don't speak English very well, if you have some difficulty communicating, etc. Everybody here will have that. So the idea is that you really ask questions at any time. OK? Have a question, ask. There's no, at this level, there are no silly questions. There's no stupid questions, nothing like this. Any question that you want to ask, that's the idea. All right? If I have to go slower because of this, then it's better that I go slower and you have your questions answered properly than that I run like hell and then you get out of here and you still have doubts that you had before. OK? Any questions? Not yet. All right. OK, so the idea is that in these 3 first lectures, I'll give you some general discussion of reminding you of how we get the equations in cosmology, how we start solving them, how we start looking at the universe in light of these equations. And so I'll lead you through first general relativity, Einstein's equations, Hubble law, some discussion about dark matter and cosmic acceleration, and then tomorrow and the day after, that camera is going like crazy. It's not finding me here. Oh, it's because I'm sitting down. Antonino, could you tell the lady there that because I'm sitting down, the camera is acting weird? Either that or has been hacked by a Russian. Anyway, so this is it here. Yes, a question already. Very good. They are already online. Well, I sent them yesterday. I don't know if they were working yesterday, they would have put it online, but maybe not. Yeah, all these slides here are online. Okay. Tomorrow I may be on the blackboard, so that's not going to be online, but then you can make notes. All right, so my 2 favorite books for cosmology are not necessarily the ones that you're going to be looking for structure formation. In fact, there are no really good textbooks for structure formation. They are all either a bit outdated or they are too technical, but these are the books for cosmology, basic cosmology that I like. So Mukhanov's book, Physical Foundations of Cosmology, and Peter and Uzan's book, Primordial Cosmology. So these are, if you want to take a look at some of the stuff that I'm going to be talking about in more detail, it's there. Also, the issue about perturbing homogeneous and isotropic universe, I'm going to be very, very superficial about this. If you want to go into more detail, cool. It's going to be here and here, OK? All right, so let's get started. So the idea is that we are really working in generally covariant theories of gravity that includes general relativity. It has been more fashionable lately in these late years to consider other theories not being not only general relativity. What? Oh, the light. Can you? Thank you. That's a better idea. Yeah, the other one. Maybe you can leave the ones in the back on. Otherwise, people sleep. Yes, that's good? All right. So there are many other theories of gravity which obey the equivalence principle. They are general covariant, so that they are based on perturbing the metric of space-time and describing gravity through the curvature of space-time. This has been more that has been a hotter topic of research recently because of the problem of cosmic acceleration, which we will hopefully talk about a little bit here today. So in these theories, the metric of space-time, the geometry of space-time, is key because it causes the motion of bodies through the geodesic equations, which we will see here also again. And it's also determined by the matter that's in the universe, right? So the question is, what is geometry of space-time, causes it, and what are the dynamical equations? Modified theories of gravity have slightly different dynamical equations compared to general relativity, and then we have to make measurements to test these theories. That's the idea. So just to give you, just to remind you how this all started, it all started when in the 19th century some mathematicians started to play around with the idea that you could have spaces which are non-Euclidean, which are still what we would call today homogeneous and isotropic, meaning that any point in this space is equivalent to any other point, and there are no preferred directions. This wasn't clear until the 19th century, and these guys, you know, Lobachevsky, Gauss, and what's his guy's name, Bolyai, started to build these surfaces, which are not only like an Euclidean surface, which is flat, but also curved. This one was known, of course, like the surface of a 2D sphere. You know that every point in that surface is equivalent, and every direction is equivalent. But what it wasn't clear was that you could find also infinite spaces, which are also curved, and that all the points are equivalent, and all directions are equivalent. But then in these surfaces, in these spaces here, the Euclid theorem that for given a line and a point, there's only one line that passes through that point that doesn't cross the other line, that this is not true here, that you can have infinite lines there. So this is how this all started, this playing with the curved spaces and then curved space-times. The idea of homogeneous and isotropic space, which is a very powerful idea, is based on the ideas of homogeneity and isotropy. And here is how you have a homogeneous surface, which is not isotropic, and here is an isotropic thing, but it's not homogeneous, of course, right? So here it's have a homogeneity, any point in this surface is equivalent pretty much, but this direction here is preferred, is different than this direction here, right? So this is a piece of wood here. And here is the same, you know, this point outside is not equal to the point inside, but all directions are pretty much equivalent. So when you put these two things together, there's only a very, very small set of spaces that can observe both homogeneity and isotropy. And these are called, and these in context of cosmology are called the Friedmann, Lemaitre, Robertson-Walker spacetimes, right? So the cosmological principle is the idea, very powerful idea, very basic. Without that, we cannot do anything, that the universe is the same everywhere and looks the same no matter where, in which direction you look at, right? So this is the basics of what we are doing here. Basically, this started people to think about generic spacetimes and how to describe these spacetimes, and then Riemann in 1884 and 1854 started to describe these these generic spaces with any kind of metric, describing intrinsically how these spacetimes behave, and then the notion of a metric and the derivatives of this metric started to appear. This is how this whole game started. It was in the field of mathematics, basically geometry, this differential geometry, right? So the metric in this sense has to be an arbitrary differentiable function, and this is how we play. So the metric, this was Riemann's main insight into this, was that if you have a surface like this which is curved, the metric describes to you how you take one vector somewhere and how you move it along some curve that you determine. And then if you take that vector and you move around that curve and you come back to the same point, okay, this transport equation here, this parallel transport equation which was described by Riemann, it gives you that the difference between the vector as you move it around in this closed loop here is determined by the amount of curvature that you have here. So the change in that vector here is proportional to the curvature as described by the Riemann tensor here, right? And by something that's basically the volume inside here. In this case would be an area, but in a generic space-time would be a volume, right? So this is how we all get started on this. And then he started with all these objects that you know today, the connections, which describe parallel transport, the Geodesic equation, and so on, the Riemann curvature, and of course you have the notions of covariant differentiation. So this is just to remind you of stuff which I assume you already know, but I'm just reminding you where we get our equations from. It's not from Newtonian physics. It's not from, we don't pick it out of a hat. We derive them from Einstein's equations. That's the idea. Of course, there's a basic symmetry in here that we cannot forget, and that is important to tell us how we manipulate our equations, which are basically the idea that you can go down to an Einstein elevator. So locally, you can always make a coordinate frame where you are in a locally Minkowski space-time. That means you do away with any kind of a gravity. You are in the free-falling reference frame. Now, the idea is that you can do this here, but if you are in a curved space-time, the derivatives of your connections here, which are which is one of the stuff that goes into this. Not my finger is on the way. One of the objects that go here in the Riemann tensor, they do not go away. So you can make the metric and the connections to go to 0 in some point in space-time by just fiddling with the metric, finding a free falling coordinate frame, but you still cannot do away with the derivatives of the connections, which are, let's say, if you want to say it, the tidal forces, if you will. So you cannot, even by choosing the locally Minkowski frame, you cannot make the Riemann tensor go to 0, and that's why there is a persistent property of space-time, which even if you go to this locally Lorentz frame, Minkowski frame, it's still there. So curvature cannot be, as we say, gauged away here by a coordinate transformation, and this is a property of all covariant theories of gravity. This is also in not only in general relativity, but in all, let's say, law-abiding theories of gravity, if you will. Equivalence principle is something that we measure very well, so it has to be there in some sense. Okay, so still in the review section here, suppose we have a space-time. Suppose we have a metric in this space-time, and then what defines freely falling observer at that point? We have to actually calculate what is acceleration here, and if you calculate what the acceleration here is in a space along a curve where there is some sort of a metric with derivatives, second derivatives, and so on, then basically the acceleration equation here, or if you want, Newton's second law, but now in the context of generally covariant theories, is what we call the geodesic equation, right? So this tells you how you accelerate some point here, some particle, some body along some curve here, along some parameter here, which we call lambda. The geodesic equation, you have to remember this. You have to always remember this because we sometimes forget this in cosmology that, if you think about cosmology again, if you're thinking about a space-time which is in some sense on average expanding, so things are moving. So if you look at 2 points, they are being separated by distances which are typically not growing with time in some complicated way. So, and it's not just that the geodesic equation tells you how the spatial coordinates are changing with time, but also they tell you how the clocks of those two observers are being related to each other. And this means that the way in which you measure time in different points has to be, the metric tells you how you relate these two times, right? So the geodesic equation tells you how the spatial and the time coordinates are being related. And usually we call proper time the x0 here, tau, along the geodesic of a certain particle, right? Now, why am I saying this? Because this is an important piece here, and I'm not going to come back to this later, but if you look at the Newtonian limit, that means the small velocities limit, weak field, that means the metric perturbation, the metric is very nearly Minkowski and so on, then what you find is that the equation for the spatial acceleration here, right, the acceleration of the spatial coordinates here is related to the component G00. So G00 plays a very important role in all of in any kind of game that you play with these generally covariant theories. And if we and if you write this G00 as basically the Minkowski value 1, and then you perturb by a small amount here, so this phi is something which is very small. Okay, so of course phi we will eventually turn this into the Newtonian potential, and here the Newtonian potential of course has dimensions, but if you divide by c squared, it is d-dimensional. And all that I'm doing here, I'm not writing this down. I forgot to write that. I'm assuming that c is equal to 1. I'm using units where c is equal to 1 in most of what I'm doing here, right? So I forgot to say that. But basically, if you write this, then you realize that you can recover Newton's, the Poisson equation here, or Newton's second law here. Basically, acceleration is equal to gradient of the Newtonian potential. You recover it from Einstein's equation. So this is critical. I'm not going to come back to this because I'm not going to derive to you the equations for the displacement of particles in perturbed spacetimes through Einstein's equation. This is too much for lectures here. But if you want to take a look at how you derive the full, beautiful, complicated set of equations in perturbed Friedmann-Lemaitre-Robertson-Walker spacetimes, you should take a look at those books that I showed you in the first slides, okay? I'm not going to do this, and in fact, I'm going to get away from Einstein's equations. I'm going to use Einstein's equations here in its full glory to derive the background for the expansion rate, but not for the perturbations. Anyway, so that's it. So here are some problems for you if you want to do it. If you think it's too easy for you, it's fine, but you can do this even faster if you think it's that easy. So some problems here. They are going to be on the website. You can download them, but just some warm-ups here. Show that for a geodesic curve, this has to be true. Find an equation for the geodesic deviation, so also called Reichaldury's equation. Show that there is a way of projecting the metric of space-time into space-like hypersurfaces. These are just some exercises in general relativity, okay? All right, yes? One more.
So you said x0 tau, right?
The proper time here. Proper time for the particle that moves along that geodesic.
So you're assuming that we are...
Yes. Talk on the phone.
So you're assuming that we are working only with massive particles, okay? Here.
With what?
Massive particles.
Yes, this only applies for,
okay.
It doesn't apply for null geodesics and massless particles, as you know. Thanks. Good point. Any more questions? Yes?
You said you only need the homogeneous isotropic to derive the Friedmann-Lemaitre-Walker metric. Is that right? You just need these two assumptions without any other further assumptions.
So the proof that with a homogeneous and isotropic space surface, that you get the Friedmann-Lemaitre-Robertson-Walker space equations, the Friedmann equations. Basically, the general proof of this was given by Robertson-Walker later on. Yes, but yes, this is a theorem. If you impose homogeneity and isotropy, you get the Friedmann-Lemaitre-Robertson-Walker metric and the Friedmann equations. Yes, that is a.
There is no need to...
Well, in general relativity, of course, right?
Mm-hmm. Okay, so you also have to assume general relativity.
Oh, yes, of course,
okay.
Yes, absolutely. If you have some other theory of gravity, you still have the Friedmann-Lemaitre-Robertson-Walker metric,
okay.
but the equations will be different because the equations will not be the action, basically. The Einstein-Hilbert action will be changed, so the dynamical equations change. But the metric has to be that metric, which I'm going to show in a second, okay?
Okay, thank you.
All right, any more questions? Otávio?
No, I'm just
No?
getting the microphone.
Oh, you get the microphone, okay. Oh, you have two microphones, better. All right, any more questions? No? Okay, so you can surely work with these exercises here if you want. So, Einstein's equations. Now, of course, I'm assuming general relativity here. I'll assume it for basically all of the time, except when I say, okay, now consider a different theory here. So we have this two-way street here where matter curves space and determines what is the metric, what the metric looks like, and the metric determines through the geodesic equations and also for a fluid, the Einstein's equations, how matter moves. So that's an important thing. I'll tell more about this, how the two are related for in case of a fluid where you don't have actually necessarily just a particle. So matter and metric, you have to get them together. You have to put them in the same equations self-consistently and find the dynamics that you have for your system there. And before we do this, let's also remember, because this is something that I don't know if Mehrdad, the lecturer that's going to talk about inflation, is going to talk about this, so I'll make a very brief detour here into how we derive these equations, how we get some basic symmetries out of them, okay? So it's still on the basic stuff here. So you know everybody knows Noether's theorem and the very deep relation between symmetries and conservation laws or conserved currents in the case of an internal symmetry. But basically, you have invariance under time translations or parameterizations that is related to energy conservation. In space, this is momentum conservations, and in rotations, this gives you angular momentum conservation. And what about general transformations like, a Lorentz transformation, for instance, that mixes up time and space? They are a symmetry as well, okay? They mix the momenta, like energy and momenta, they get mixed, as you know, from even special relativity. So these kinds of transformations here tell you how a vector such as the momentum, the form momentum, gets transformed. So let's just remember how this is done, because this is going to surely appear in Mehrdad's lecture. I suppose if he's going to do inflation, he's going to have to talk about these derivations. So if you have a Lagrangian here, which is just, so this is a classical point particle Lagrangian here. The action is just the integral of this Lagrangian, and then we assume that it's just given by some simple function like this with a standard kinetic term. So this is kinetic energy and the potential. And then we can make some sort of a reparameterization here of time that changes both the coordinate and the momentum of this coordinate here. And then we say that between a starting point and an end point, you can take any two paths, okay? Now, demanding that these two paths don't affect, that the action is invariant here, it doesn't matter how you get from point A to point B here, you demand that this variation of the action is 0, then you get that the variation of these guys is just given by the partial derivatives with respect to variation in Q and the variation in Q dot here. This is just to remind you how we make this calculation. Then, of course, you use this here in the variation of Q and Q dot, okay? And then you get the Euler-Lagrange equations, which are in here. You make an integration by parts before you do that, of course. An integration by parts here, and delta t here in this Q dot between initial and final point is 0. So you get basically the idea that this is 0 here. So this is basically the idea that you have energy conservation here, okay? So the energy is conserved between point A and B in this picture here. So that's energy conservation, so we have basically a global symmetry here. Basically, the same idea is you're going to use for general relativity. You're going to make a general variation with respect to the underlying variable that you have, which is the metric and its derivatives. Now, you play this game in a much more complicated way. If you have done this calculation before, you know it's kind of a long, it's a slightly long calculation, but not that long. Now, what I'm going to remind you here is that we have a symmetry here. I'm not going to derive the Einstein's equations here through the variational principle. I'm not going to do that. I'm just going to, I was just reminding you how you get equations from variational principle. But I'm going to remind you that there are symmetries and that your theory has to be invariant under those symmetries. And those symmetries for generally covariant theories, including general relativity, are coordinate transformations. Coordinate transformations are, they shouldn't make physics any different. So let's remind what they are. So if you change the coordinate between x and x prime by some amount psi here, now the metric using these the indices up, that's these contravariant indices up here, they will change by this amount here, and of course this here is a delta function here, the delta of mu and alpha, plus the derivative of mu with respect to alpha here, so and so on, right? So if you put this inside here, and you open this up, and you assume that this is a small change of coordinates here, then this gives you some change of the metric in your equations. This should be a symmetry of your dynamic equations, right? And of course, if you have also, by the way, before we start playing with this, if this turns out to be 0, if these covariant derivatives of this displacement here are 0, then you have something which leaves the metric invariant. So on the way to prove the question that you just asked there, if Friedmann, Lemaitre, Robertson, Walker are the only spacetimes that preserve homogeneity and isotropy, you can start with this three-dimensional space with constant curvature here, and you can show that displacements along, that displacement that corresponds to translations and rotations are these so-called Killing vectors that leave the metric invariant. So that's an exercise for you that basically proves to you that this spacetime here preserves homogeneous and isotropy. It doesn't tell you the other way around that they are the only spacetimes where this is true, but at least it tells you one of the ways of this theorem, right? Okay? So how many Killing vectors you have here? Of course, by what I just told you, it has at least 3 plus 3 translations plus 3 rotations for the 3 Euler angles of the rotations. And this is basically the amount of symmetries that you have in this space here. Okay. Okay, so if the dynamics of matter is independent of this coordinate system, and we can demand that this is a gauge symmetry of any generally covariant then the counterpart in matter, because remember, matter has to be coupled to geometry through some dynamic equations, for instance, Einstein's equations. So the matter action should remain invariant under these kinds of transformations. So this is a very, very basic demand on the matter side now, not necessarily on the metric side here, right? So let's assume that we have, I don't know why, oh yes, I'm going to use this later here, but let's assume we have a matter action in 4 dimensions here, of course. We have to have a square root of minus g for the volume factor, with some matter Lagrangian here. And let's say that we demand that the matter action should remain invariant. What does happen when we change the action here by that delta g of the previous slide, which is generated by a coordinate transformation here, okay? Usually we assume that this Lagrangian here doesn't depend on the derivatives of the metric. Of course, this square root of minus g can come out of this, but basically, why is it that the metric does not depend on the derivatives of the metric here? Why the Lagrangian of matter doesn't depend on the derivatives of metric? Usually this is the case, yeah, right? Just think a bit why we do this. It has to be, I mean, it's really weird to think of a theory where this doesn't happen, but anyway, we throw away this term here, we assume that this is 0 usually. So we are left here with this derivative here, and the idea is that basically you open up this guy. This metric perturbation here is the one that I showed you before in the previous slide, right? Is what you generate by a coordinate transformation. And here, we call this derivative here, okay? What we call a tensor which is called the energy momentum tensor here. And basically what you have here is this combination of these displacements here. However, if you notice that this covariant derivative here, you can integrate by parts here, okay? Right? So basically just using the associative property of the covariant derivative. And then if you use these properties here, you find that this is equal to that point here. So this is a derivative, a total derivative, and a part here which is coming from this guy here, right? So we have two pieces. Now, this is just like what we had before. You can integrate this by parts. You can integrate this by parts, take the volume to infinity, or just do anything else. This you can get rid of by integrating out, right? What you have left here is some derivative of this object here, okay? So notice that I flipped, I took the two indices mu and nu up here, and I took these two indices down here. You can always do this, as you know from your general relativity classes, but what you're left here is this covariant derivative of this energy momentum tensor, which has to be 0. So this is telling you that there is a conservation law here, which is basically the same as saying that energy is conserved, momentum is conserved, angular momentum is conserved, and many other things are conserved, in fact, in a more general, broad sense. So this is what we call energy momentum conservation. And it also tells you how you get some sort of an object out of your matter Lagrangian that expresses energy and momentum. We just have to go back now and look at this object and interpret it so that we can get out the usual stuff that we want to think about. We want to think about energy, momentum, stresses, angular momentum, etc. We want to go back now in this energy momentum tensor and remember how we get energy, momentum, stresses out of it. Okay, so let's do this. So this is the energy momentum tensor here. Instead of looking at the formal expression and then extracting what we need, I'm going to build an energy momentum tensor from basic quantities for a fluid, like the velocity of a fluid, the energy density, the pressure, and the stress of that fluid, okay? So this is a very schematic way of doing this. You can find more about this in many of your standard textbooks, but if you have think of this as an element of a fluid. So think of a fluid that fills this whole city, the whole solar system, the universe, and a little piece of it is inside this box here. So that fluid has what? First, energy density, or if you think of a fluid, just mass density, right? Just the density of the fluid, mass per unit volume, for instance. This turns out to be in the 0, 0 piece of the energy momentum. Now think about this. 0, 0 piece is related to time and time is related to energy conservation, as we saw from just the first application of Netter theorem. So it stands to reason that T00 is related to energy density, and it is, in fact. It's what we call usually energy density. Now, think about now the pressure that a fluid inside this box exercises on all sides equally, or on all sides, let's say, in sides in the x direction, y direction, and z direction here. So the pressure normal to the surface. So this is what so the diagonal components here is what we call pressure. It's how this gas or fluid, if you want, exerts some pressure on some imaginary boundary. So if it is a gas, it tells you if that gas is going to expand or if it's going to contract or if it's going to do anything, right? But there's more than this, of course. You can also have stuff like this. You can have also that the gas is moving in ways like this, or like this. You could be deforming this volume in some way. So the energy density doesn't tell you anything about deformation. The pressure will tell you how your volume expands or contracts as a whole, but there are other components that are telling you how your volume is twisting or shearing. So these other components are, let's say, the off-diagonal components of the spatial parts of the energy momentum tensor. So the symmetric traceless part is called shear, The antisymmetric part is called the anisotropic stress, or it's related to this actually, because the energy momentum is symmetric, but you have an antisymmetric object that appears in there. And you have the energy flow, of course, if this whole thing is moving somewhere. Of course, it's taking the whole fluid and taking from here to there. This is energy flow or momentum, if you want. So this is, again, in close analogy with what you have in, for instance, the Poynting vector of electromagnetism that moves. It corresponds to momentum density, but also to an energy transfer from one point to another. So that's the energy flow, or the momentum that is crossing some surface I here, okay? So this is basically how you build all of these, of the physical quantities that you can think about on the basis of the energy momentum tensor, and also start to thinking about a system where you don't necessarily have particles, you have more than particles, you have a fluid. A fluid is more than a particle because it is not just described by the way in which each particle is occupying a space here. It doesn't have only energy. A particle, of course, only have some energy and some momentum, but a fluid has more than this because it's all particles together and they're interacting in some way and they are hitting each other and they are bumping into each other. So a fluid has many more degrees of freedom than just a particle, and in any description that you have which have a continuous field, be it matter or scalar field or whatever, you need to have more degrees of freedom in your energy momentum tensor, and this is what we have to deal with, right? So basically, the conservation of this energy momentum tensor here, which is demanded by the gauge symmetry of your gravity side, ensures that there is something called energy momentum conservation, okay? Okay. So, yeah.
Maybe I don't understand, but did you say that we always have conservation of energy and momentum?
No, it's the energy momentum tensor conservation, okay, which is, I didn't write in here, but it was in here, right? Sorry. Here. This. I should have stressed this.
It's just
okay.
Because you assume that your Lagrangian is variant under coordinate transformation, so I started thinking that maybe you have killing vectors for each direction, and then you have conservation of each quantity. But it's not the case.
Well, the killing vector will not change anything on the dynamical equations of gravity. If it is identically zero here, then you cannot even build an energy momentum tensor, of course. But the idea is that in these calculations here, you use a general vector, not only a killing vector. When you do the variation, you find that this equation has to be true. It doesn't mean anything that if you choose a specific vector, it doesn't mean anything in terms of the energy momentum tensor itself. Although it is true that if you have an energy momentum tensor that is, if you have an equation that you have matter and metric here, and you have a killing vector, it will be generally true that if you get a killing vector and you go to the energy momentum tensor, it's also true that that energy momentum tensor is probably going to be unchanged if you go in the direction of that killing vector. I haven't thought too much about it, but it must be true. It must be true. If the left side doesn't change, the right side won't change either, right? Okay, so this gives us, let me go here, gives us a bit, I mean, it gives me, I don't know if it gives you some more intuition about the energy momentum tensor. Let's give a bit more thought about this by looking at Minkowski spacetime and looking at a fluid at rest without any stresses, so very simple situation, basically a gas inside a box. The 0,0 component is the energy density, right? The ij component has an isotropic pressure, and it's Kronecker delta, meaning that in any direction x, y, and z, the pressure is the same. And the flow of momentum is 0 because you have this fluid at rest. If you were moving this, then this wouldn't be 0. You would have a velocity there corresponding to taking that fluid in some direction. And then the fluid velocity here, you can ascribe a fluid velocity, would be just of a particle at rest, which is just 1, right? that is the forward velocity of a particle at rest. And then if you have a fluid element, that is also going to be at rest. So you can actually write explicitly, in terms of this forward velocity, an energy momentum tensor here in terms of the density and the pressure, and this U here, and the Minkowski metric here, right? So in this way, you can always recover 0, 0 here. You have P here, which is 1, 1, and this eta 0, 0 is minus 1. So this cancels out the pressure for 0, 0. And then for Ij, this is 0, and this is just delta Ij. So you recover it. And it turns out that this is a more powerful description of a fluid than we have even for Minkowski. It turns out that this is something that you can generalize. You can have a fluid now which is moving. Velocity is non-zero. And this is the energy momentum tensor of a fluid even outside of this simple picture that I gave you here. So let's consider a fluid in motion here. Okay? So let's replace the forward velocity here by what you have a forward velocity for. Think of a particle. Now it's a fluid. You can think of that fluid as having a velocity, energy, momentum, energy and momentum. So the forward velocity here is just given by the gamma factor of a certain velocity v here. And then you have this expression here for the energy momentum tensor. 0y is this this factor here. So remember, gamma is square root of 1 over 1 minus v squared over c squared, and we're using c squared is equal to 0. And this is Tij here. And then you can calculate what this conservation, so here we're talking about Minkowski, okay, still. So the covariant derivative of the energy momentum tensor, 0 component, is given by just normal derivative. And if you calculate that, you get this equation here. Now let's look a bit more carefully. Okay, so maybe I'll look at it later, I don't remember, but this is the equation here for conservation of energy momentum. And this turns out to be basically equivalent to the continuity equation, basically, but now perturbed, okay? We're going to come back to this later, all right? Because we're going to look at not only a homogeneous and isotropic universe, but but one in which there are small perturbations. So there is a small perturbation in density, in pressure, in velocity, and everything, okay? So it's so we're going to come back to things like this, right? By the way, if you do the spatial components here, it's an interesting exercise. And you're going to get something which looks like Euler equation, which we'll also going to see here later. Okay, Euler equation is just the hydrodynamic equations for a fluid, and we're going to come back to this later. All right? Yes, there's a question there.
You gave an interpretation for the energy momentum tensor, but it is defined in terms of a derivative of the Lagrangian.
Yes.
And you have a freedom in determining the Lagrangian.
I have what? Freedom?
Yes, in determining the Lagrangian, right? So.
Well, in which sense freedom you mean?
At least for a total derivative. And you get the same equations as motion.
There is a total derivative term that you can integrate out, yes, but that doesn't depend on what kind of matter you have. It's not a freedom. It's just integrating out. It's mathematics, not a freedom in terms of physics.
Yes, but you would lead to a different energy momentum tensor if you choose this different Lagrangian.
Sure, of course, but it has nothing to do with the total derivative, okay? Of course, different. Okay, let me put it like this. If you have dark matter or neutrinos or a scalar field, each one of them has a different matter Lagrangian, and they will have different energy momentum tensors, yes.
All right, but...
The idea is that you put everything together, and matter is, the stuff that matters to gravity is you put all the matter in there, because all the matter gravitates. Of course, each one has an expression. Sorry, go ahead.
Yeah, but for the same kind of matter, you can have different Lagrangians and get the same equations, right?
Well, how exactly you would have different Lagrangians and get the same equations there?
I think just an example, when you define pointing
if you get in Lagrangian something which is a total derivative of something like this.
No, it's just that, for instance, in electromagnetism, when you define
Yes.
the Poynting vector, you can define it minus a total divergence, and still the conservation equation for energy is the same. So I think you have some arbitrary thing that you can sum as a total divergence.
But if you have a total divergence, it will come out of exactly in the same way when we started the calculation, that you integrate this, you get this out. The equations for conservation of energy the energy momentum tensor will still be the same because you integrate that term out, right? The action will not change. The idea is that you're making a variation of the action, and with those terms, you don't change the action.
But I think her question is related to the fact that you're trying to interpret a local conservation equation, not an integral one. So if you do that, you always have this arbitrariness in the definition of the energy momentum tensor. Right? Just like the Poynting vector. If you think of it as a energy flux, you can always sum a total divergence, and what does it mean, this total divergence?
I don't know what happens with the interpretation of the...
I couldn't hear you, sorry.
I don't know what happens with the physical interpretation of the energy momentum tensor because of this freedom in its definition.
I have to say that I didn't think enough about this.
Okay.
But I have the impression that I think that the energy momentum tensor will not change in the calculation that we just did. But you might have additional terms which are, let's say, charges which are not, that don't connect with anything else, any of the energy and momentum components, and you have something else which is conserved, but it doesn't talk to the other components. This you might get something like this, like a conserved global quantity that doesn't talk to the local equations. Yes, you can have something like this. You can always have, but in the context of a matter Lagrangian changing in that way, that's an interesting question, but I never thought about this. But you may have a global charge, but doesn't talk to the local conserved quantities. Yes, that's a good point. Okay, all right. Okay, so let me summarize here for you. Let me see how am I doing with time. So just to remind you, so this is a mnemonic way of looking at the energy momentum tensor here. This is from Bain's lecture here on general relativity, which is very useful also. I can make the link for you guys later. So the time-space components are energy flux. The time-time component, energy density. Pressure here, shear is there. Okay, so that's basically a way of you to realize how a completely general fluid is going to play out in the energy momentum tensor there. Usually for cosmology, we don't, sometimes you consider shear, but in a different context. Momentum density is also something that's usually typically small. Most of the game is being played by these diagonal components here. Okay, so it's simpler than what you would think by looking at such an object. But this is what describes matter in principle. So let's go back to that equation that I showed you before, the continuity equation here. In the non-relativistic limit, let's neglect the order v squared terms. And this is just giving us, basically, so I'm throwing away some of the stuff here. Of course, if you wanna do some more detailed calculation, for a relativistic fluid, you don't want to do this, but if you throw them away, then you have something which is what you see here, and this is basically what you remember as being basically the continuity equation for a fluid. So this is basically also, you can you can say this in terms of energy conservation, or in thermodynamics, dE is equal to minus PdV. And if you write this out, this is basically what you get here. This divergence of the velocity here is just going to give you how your volume is being increased or decreased there, right? So this is this term here. So what you see here is that from the energy momentum conservation, you get back some equations that tell you how matter should behave. In fact, this is even independent of the general dynamic equations that relate metric to matter. This is a more basic consistency relations. So these energy momentum conservation are even more basic than whatever theory that you have. So Remember, this is here independent of whatever theory of gravity you have. All that we demanded was that you have these general covariance or gauge symmetry with respect to those coordinate transformations. So we will see later, and we will come back to this when we do start to make perturbations of space-time, that you get energy conservation. You have fluid equations like Euler equation, and we're going to come back to this later, okay? I'm not going to derive these from the energy momentum conservation. This is a much more time-consuming exercise, and I refer you to those textbooks that I gave in the beginning. I'm going to basically start with, let's say, a description for the Euler equation and energy conservation equation that incorporates some features of general relativity, but not all of them, okay? So it's basically a pseudo-Newtonian one. An exercise for you to do that has to do with what we've done here is take a scalar field. By the way, this is Mehrdad Mirbabai's issue. Here he's probably going to give you some similar exercise, but you can already start thinking about it. How with a matter Lagrangian, which is that for a scalar field, which is described here, find the stress energy tensor, find the equation that that scalar field has to obey, which is called the Klein-Gardner equation. Find also the Klein-Gardner equation directly from the variational principle in terms of the scalar field itself. So vary this equation here in terms of the scalar field, not the metric. Then ask yourself if you could write that stress energy tensor of the scalar field in such a simple way as we did in here. And that's an interesting exercise. It doesn't matter if you're a beginning student or a more advanced student. This is an interesting exercise to make, okay? I don't know if Mehrdad is here. I don't know. There you go. Oh, hi. I'm Raul Mehrdad. Nice to meet you. I don't know if you're giving an exercise such as this, but probably at some point, right? In any case, here it is. They can solve it at some point. I'm starting from the very beginning here. And another problem, electromagnetism. Find the Maxwell's equations. An interesting exercise also that in 4-dimension vacuum electromagnetism is conformal invariant. Actually, it's a very general statement here. Show that the equations in vacuum are invariant under these transformations. This is an interesting exercise to show that electromagnetism is conformal invariant. This also has some impact for inflation theories, an interesting impact as to how you can make inflation with some fields but not others. So finally, Einstein's equations. Okay, so what are the equations we have to deal with? Basically, for general relativity, you have the Riemann scalar here, which is the contraction of the Riemann tensor that we saw here before, and the matter Lagrangian. And if you vary that with respect to a general metric perturbation, you arrive at Einstein's equations, which are, as you know, here. So basically, Einstein tensor, energy, and momentum. Of course, I'm not going to work with this in any more glory than basically the basic homogeneous and isotropic case. When we do perturbations, I'm going to refer directly to the Euler and continuity equations. I'm not going to do large-scale perturbations. I believe that Mehrdad will probably do that. So he will talk about this, but in a different regime and case than we are interested in for large-scale structures. So those are all related, okay? But for a hint of how this, for an idea of how you derive these equations in the case of large-scale structure, you should pay attention to Mehrdad's lectures. Okay, so basically we start with Einstein's equations, which are here. We impose homogeneity and isotropy. The metric now has to be given by a Friedmann-Lemaitre-Hobson-Walker metric, and matter has to be described by a homogeneous and isotropic fluid, if you want. So energy and pressure are just given by some functions of time. They cannot depend on position because all points in space are equivalent. So there can't be any dependence there. And then, okay, so what is this metric that we impose? So this is a theorem that was proved later in the 1930s by these two guys here, but it was shown by these two guys that describes cosmology. So what is this metric? This metric here in very simple terms is given by something like this. The metric is given by basically time doesn't, there's nothing happening to time here, but the spatial surfaces are being changed with a universal function of time, which we call the scale factor here. Of course, the scale factor is a function of time that you can always multiply or divide by any constant that you want. This is just some, you can multiply or divide by anything that you want here and incorporate this into redefinition of your spatial variables. So we define this scale factor such that today at t0, that means today, this is 1. So this gives you a relation between these coordinates today and sometime in the past when this a was smaller. So what do these surfaces look like? Well, these are exactly those surfaces that I told you about in the beginning here that started to be studied by Lobachevsky, Gauss, Bolyai, etc. in the 19th century. And there are 3 of them, but there's a continuous parameter here that describes how you go from this to that, which is called the spatial curvature. Now, we can write in some coordinate frame this here, okay? So this r here is, the way that I wrote it is stupid because r has dimensions. It's like distance, right? So what it should be here is really r over some r0 or some k inside here. So k is equals to +1. There's a k here. There's a k here. Okay? And k is equal to 0. You just come back to the usual Euclidean surface. So this is it. There is some constant which you can express it as k, or better, with dimensions, with some spatial curvature radius, which I call r0. And in this case here, has a signal minus, and you have the closed surfaces, spatial surfaces. And if you have a signal plus here, you have the open infinite surfaces, right? The open spaces here. In either case, you have a spatial curvature radius, which is a better way of expressing this. The curvature really doesn't have dimension. It's not really a dimensional. Spatial curvature has dimensions of 1 over radius squared. Usually in textbooks, in many textbooks, this is not, people just say k is equal to +1, -1 is 0, but it's not really. It's just a parameter here, r0, that you can go from something very small to infinity. And this is, let's say, a constant of nature that we in principle don't know, or it is set by some process in the early universe. See the inflation lectures. So there's some spatial curvature radius here that appears that has to be there if the universe is approximately homogeneous and isotropic. It's a constant of nature. We don't know what it is. We have to treat it as something that we don't know. Okay? So basically, this k here is something, it's the very first thing that we're going to try to measure in the universe or to relate to some dynamical process that's happening in the universe. Okay? So that's the spatial curvature, and we have to deal with that from the beginning. The good news is that it appears that, at least today, this radius of curvature here is so large, that we can effectively neglect these 2 cases and work to very good approximation with an Euclidean spatial surface, which is this one, which makes the calculations a bit simpler. But if you want to do really a thorough test from the beginning of all the properties of the space, of the universe, of cosmology, you have to consider that spatial curvature has to be there. And if it's not there, you have to explain why it's not there. And for this, again, you go to Merdad's lectures, okay? For a good explanation for this. Now, there are different ways of expressing the three-dimensional metric Robertson-Walker metric, okay? So there are different names going around, okay, people? But this is, as far as I know, more standard here. So this is what we call polar coordinates, okay? All right, so if k is equal to 0, you just get the usual spherical coordinates that you're used to. By the way, in all of these coordinates, you get the spherical coordinates that you're used to here. You also have what we call hyperspherical coordinates, which is, you turn this r here into this function here. By the way, even if k is negative here, you get an I here and an I there. This turns into a hyperbolic sign. You don't have to do anything. It's already automatic in this way here, okay? And then this hypersurface becomes simpler because you don't have a funny term here in the radial term. The funny term gets switched over to the angular part. And this is the more popular choice, because if we're looking at stuff which is radially away from us, okay, a galaxy which is at some radius from us, we choose ourselves as being the center of the coordinate frame. Even if we are not in the center of the universe, we can always choose ourselves to be the center of the coordinate system at least. And then this becomes simpler. This is the most popular choice, and this is what we call the Comoving Radius here. And also you have the conformal Cartesian coordinates, which for many calculations, it's actually pretty useful to calculate because it's related to basically Cartesian coordinates here. And here, you can see why this happens, because now this is basically, you can write this as dx squared plus dy squared plus dz squared, and this is symmetric. All the three components, all the three spatial components are similar, but you still have this funny term here. So this is more obvious to see that the spatial sections are homogeneous and isotropic. Actually, they are all, but sometimes it's you write in different ways and you see things in different ways. So this is also a popular choice. So like I told you, the most common choice is the second one here. Okay, and unless I explicitly say otherwise, I'll be working on that one, and I understand that most people will be working on this hyperspherical coordinates here. More problems for you. So show that in hyperspherical coordinates here, simple to calculate, you have a 1 plus 3 simple decomposition of space-time. This is simple. Show that the Riemann tensor is given by this very simple thing here. Okay? This is a good exercise. Okay? So the three-dimensional Riemann tensor is given by this, so this is a good exercise. And also that the 3D volume is given by the determinant of this guy here. And calculate the volume of a 3-sphere. Anyway, so these are just exercises that you probably did sometimes years ago, but So, now, what do geodesics look like in this space-time? So, I need to get some water here. I'm sorry that I'm sitting down, but really. Any questions so far? More questions? I'm talking very fast. I do this a lot, but don't get intimidated by my. I'm trying to. I don't even know which slide I'm in. I'm slide. Ooh, Jesus Christ! I have to go faster. Anyway, but no, like I said, it's more important that you ask questions. Okay? More questions? No? Okay, so let's go. Let's remember what a geodesic in this space-time is. So let's use here this conformal Cartesian spaces here. The connections, you probably calculated at some point in your lives, but here they are. By the way, this helps you with some of the exercises that I put before. Okay? You can also calculate the Riemann tensor for this for Friedmann-Hellmeister-Walker. So let's look. So this is an important test here of our intuition. You heard many, many times, oh, the universe is expanding, it's homogeneous and isotropic, and it's expanding. What is this in terms of, you put a particle somewhere. It's going somewhere, you guess, right? Because it's expanding in the universe, so what's happening with the particle? So take a particle which has some coordinate here. Okay, remember what the coordinate is here, okay? X here is the coordinate, the x, y, and z here, xi, x1, 2, 3. And the scale factor is outside, so this x is what we call the Comoving coordinate. Suppose that we have a particle at rest initially here. So initially, the fall velocity is given by this. Of course, it doesn't have any spatial part of the fall velocity. And the geodesic equation here is this one here, right? If you solve this here, if you write this, you have this set of equations here. And if you solve this sort of set of equations, okay, if you use the connections that I gave you in the previous slide, and this is an exercise for you, you find that this is the solution. That you get that the particle which is at rest remains at rest. So if you give some Comoving coordinate for this particle, which is here, the universe is expanding. The physical distance between you and that particle is increasing. However, in terms of the coordinates of that particle is at rest and it remains at rest. So that's what it means to be in this expansion. The coordinate of that particle is fixed. The physical distance, of course, which is the scale factor times the comoving distance, that is the thing that is changing, right? So this also gives you an idea of if you start with a homogeneous and isotropic universe and everything is expanding in some way, the points where you put the particles such that it has a homogeneous and isotropic distribution of matter, they don't change. They remain the same. Okay? Yes?
I don't know why do you call it, why you say that the universe is expanding? Because you picked up a particular kind of particle, which is moving, like comoving with your coordinate system.
Yeah, I'm assuming that time was moving. Of course, I haven't yet said anything about Hubble law, and I haven't said anything about what's happening with the space-time. I mean, could it be that in the beginning there, the universe contracted and then expanded? Could be, in that case, that that distance will be getting smaller, and then if it expands, it gets larger. The thing is that the coordinate doesn't change. The comoving coordinate doesn't change. So that is a solution of the geodesic equation.
Yeah, but if you had choosing another fluid, like not comoving with your coordinate system, you would have a different kinematic, right?
That is very true. I could have very easily chosen a coordinate system in which the universe is not homogeneous and isotropic, at least not manifestly homogeneous and isotropic.
And in the same space-time.
Of course, in the same space-time, okay? Then every Einstein's equations, my dynamic equations, my continuity equations, and everything would be much more complicated, and I could solve them. And in that coordinate system, I don't even know what could happen. Anything could happen in principle, right? However, the fact that there is a coordinate system where that coordinate is fixed, okay, tells you that in some, at least in that coordinate system, the interpretation can be given as I told you. As in any physical system, you can always go to a coordinate frame in which your system, which is very simple, becomes very complicated. Okay? So Friedmann-Robertson-Walker is the, let's say, the minimalistic system where the universe has its simplest manifestation. You can always use different systems. I'll give you an example. Okay? We could have chosen, and in fact, we are in a system where we don't see the universe as exactly homogeneous isotropic. In fact, if we look at a certain direction in the sky, basically the direction that points at the Virgo cluster, the universe is a bit hotter that way than it is that way. So it's not really homogeneous and isotropic. It's just a small effect, okay? But it's hotter that way. I don't know if Virgo is really that way. I haven't. Let's suppose it's that way, okay? The universe is a bit hotter that way than it is this way. It turns out that if you include the motion of the sun around the galaxy and the galaxy towards Andromeda and our galaxy and Andromeda towards the Virgo supercluster, you get a speed which is in that direction. So we see the sea of radiation called the cosmic microwave background. We see with a Doppler effect, so it's a bit hotter that way, just a tiny bit. However, okay, when we take that away and we move ourselves to our coordinate system where we don't really have that speed, then you get back to exactly a system where the universe is approximately homogeneous isotropic. There is such a system. That is the point. We are not even in that system. We are slightly out of there. But we have the ability, and we can be smart enough to transform to a system where we do see a homogeneous and isotropic universe approximately on large scales. Of course, on small scales, it's not. Of course, I'm here, you're here, there's the sun, the earth, and the galaxy, and so on, and the universe is not on small scales homogeneous and isotropic. So thanks for the question.
In large scales, do you know if I have an arbitrary set of geodesic of free particles, they will expand? Or if this is
I don't know how to make a general statement for a general coordinate system in the same way. I'm not smart enough to make that statement. I don't think. I mean, you can cook up any kind of coordinate system, right? I mean, You
Yeah,
can
but,
literally make any coordinate system that you want in which the universe will be far from homogeneous and isotropic. And I don't know what's going to happen to each particle in that system. I just tell you that if you describe those particles in this system where you have the Friedmann-Hobson-Walker metric, so if you go to that coordinate frame, then they will be at rest.
Okay.
Okay? All right. So, problem number 9. Consider now a particle which is moving some initial peculiar velocity. That means that suppose that all the universe is homogeneous and isotropic, but you have a small test particle with a small mass that's kind of moving. It doesn't really, it has an initial speed which is like this. What happens to that particle? Solve the geodesic equations for that particle. Find what happens to that speed, that V0. You will find that that V0 will decay. All right? So it's like the physical velocity that you gave to that particle becomes, if the universe is expanding, that physical velocity is going to be basically damped. Okay? That's going to be becoming less and less relevant. So that's another exercise for you to remember what happens to the velocity terms that you have in fluids in general relativity. Okay. So after 1 hour, I come to Friedman's equation. Perhaps I should have started with Friedman's equations, but I thought that it was important to give some background in general relativity here. So anyway, if you do the exercise that I told you before here for Friedmann-Hobson-Walker metric, you write Einstein's equations, you get the fluids from the energy momentum tensor, you put the two of them together, you get Friedman's equations. Basically, so we're using the cosmological principle, using the metric of space-time, which is this one here, and then we have Einstein's equations, okay? So basically, that's the idea, okay? Now, what are the Friedman's equations? I'm not going to write them in full because it's not useful necessarily, and we don't usually do that. I'll write to you the first Friedmann equations, which tells you that the sum of all energy densities, including the curvature here, is basically the expansion rate given by the Hubble parameter square. So that's the Friedmann first equation. And that's the most important one. That's the one that you're going to be working most of the time. And this tells you that how the matter content determines the expansion rate. Notice that this is h squared. So in principle, this could be expanding, that means h positive, or contracting, that means h negative. Equally here, but observation tells us that at least today and for the past basically pretty much almost all of the history of the universe has been expanding. So it tells you that there's a balance between the two, but that balance is affected by spatial curvature. And of course, spatial curvature can be positive or negative because there's a k here, and that k, remember, can be positive or negative. So for positive or negative k, you can increase or decrease h squared for the same amount of matter. So this is how Einstein's equations tell us that we can balance the amount of matter with the amount of expansion. Now, this is not the whole story. There is another piece of Friedmann's equations, which I'm not writing here, but that piece is equivalent to combining this equation here with the continuity equation, which is here. Okay, so these two form a complete set for you to describe what's happening with the expansion rate of the universe given a certain matter content. Okay, so the matter content has to be also defined in some sense. You have to say what kind of matter you have. In simple cases, for cosmology, let's say late-time cosmology, we do this in terms of an equation of state here that tells you what kind of pressure you have for the amount of energy that you have. So, for instance, cold matter is matter that has no speed. It's like a billiard balls scattered around the universe. They don't have any pressure, so pressure is 0, and this equation of state is 0. Now, for radiation, relativistic matter, so they have no mass, and the momentum is equal to the energy, and because of equidistribution, that momentum is basically distributed in all directions equally, so the pressure is 1/3 of the energy density because of the three spatial directions. So this W equation state for radiation is 1/3. Now, we can rewrite this in terms of this equation here, right? So we can eliminate P in terms of W times rho here, and we have the continuity equation for each type of matter independently. Now, if you have interactions between these different types of matter, then this becomes a bit more complicated, but I'm not going to be talking about interactions between different types of matter here, okay? In the simplest case, each component of your matter fields, they obey an equation of state, continuity equation of like this, or if you write in terms of an equation of state like this. So what you have is that these two equations, you can solve them, you can, given a certain matter content, find what is the expansion of the universe like. And that's what we do. And we test this by observing, for instance, the expansion rate here, by also checking when we can, how much matter there is in here on the left-hand side, by doing these kinds of cross-checks. Of course, we use as a consistency relation here the continuity equations and so on. This is for homogeneous and isotropic expansion. Now, I think I'm going to go through this very quickly, okay? This is just to remind you where redshift comes from, okay? So this is basically the idea that you have the space-like distances between the two particles. If they are at rest, how they are being, how the expansion is moving them apart is also telling you how you take, how you relate the time, your time parameter between those two distances. Okay, I'm going to go quickly over this, but if you guys ask, if you guys want, I can come back to this later because I'm running a bit late here and I've been a bit too ambitious with my lectures here. So I'm going to, I believe that this is something that you guys already know. So I'm going to, oops, let me just find here. Okay, so this is the basically the derivation of redshift. I'm not going to talk about this because I believe that redshift is clear for everybody here. If it's not, sometime in the afternoon we can come back to this, okay? Ask me if you have any questions about redshifts and so on. I'm going to jump through these slides here of redshift, etc., and come back to definition of distances because this is important here to what we're going to do, and for large-scale structure also, okay? Okay, before I solve Friedmann's equations, which, by the way, we don't even need solving. They are so trivial that it's like overkill to solve them. But let's define what distances we can measure in an expanding space-time, because different measurements will have different physical meanings. They're done in different ways, and they have different, they can be understood in different senses. So the first thing we can try to measure is what we call angular distance. Suppose that we know, I have my little ducky here, and I put duckies around the universe, and I know the size of these duckies here. I know how high they are, okay? I know their height here. And suppose I observe them at some distance such that the angle that this ducky occupies on the sky is delta theta. Why am I doing this here, really? Because, of course, in cosmology, you cannot go to whatever a galaxy is. The distances are too large. We have to rely on stuff like this little duck here. We have to rely on objects whose physical sizes we know from other parts of physics, from other parts of cosmology, such that we can measure distances. So the idea here is that by measuring this delta theta here, and by knowing what this height here b is, we can infer what the distance is. Now, this angular size inferred distance is called the angular diameter distance here. So we define this angular diameter distance by the ratio between this physical size here of this object and the angle it occupies in the sky that you're measuring. Okay, so you measure, say, a galaxy which is spherical, say, and the radius of that galaxy. Suppose you know this from something else, and you measure that angle, and you know, and then you say, okay, the angular diameter distance to that galaxy is this here. Okay? Now, how do we get this angular diameter distance here if we work at the level of our metric? Okay? So, remember that if you're measuring a distance between these 2 points here, you're doing an instantaneous measurement between two spatial points which are at the same radius, but at different angles. So your d omega or d theta or d phi, whatever the angle it is everything that you have there. Okay, so this d theta here is going to be here. Basically, this is going to be d theta square here, right? All right? So your ds square is just given by this piece here. This is 0 because dr is 0 and dt is 0. It's an instantaneous measurement of an object at two radius which are the same, so dr is 0, but in two different angles. So your ds square is this guy here. So you have a square, r squared, d omega squared. So basically what you're calling dA here is a times r, right? This a times r is what you call this distance here, okay? Okay, so a, now I didn't write to you here because I skipped the redshift part, but a, if you write this in terms of redshift, this is also something I assume that you know. Redshift 0 means that you're measuring something which is right here, so it's not expanding. So the wavelengths and frequencies that you measure here are the ones that we call rest frame, but as they are far away from us, we measure some redshift, and then you have the scale factor. So basically, your angular diameter distance is given in terms of this r here, so a times r is what we call b. So basically, dA times d theta is b here, right? So ds squared is equal to b means that dA is equal to a times r, so it's r over 1 plus e, okay? So that's the angular diameter distance from the metric. That's how you get it. It's not from cooking us something else. It's from the metric, okay? By the way, has nothing to do with general relativity, this, right? This is just Friedmann-Haber-Walker metric. You can also write this here in terms of those hyperspherical coordinates, and what you had is this guy here. Now, this is, even though it looks worse, this is better because the sky here we can relate to the, let me write this in here because I also skipped over this. So, so if you measure a distance between us here at the origin and any galaxy which is somewhere which has a redshift z here, right? So because light moves in no geodesics, that means dx squared is 0, right? Then if you have a galaxy here at some redshift z, then you have that because this is 0, okay, and you're measuring something radially, so this is 0, radial, so radial, my letter is terrible here. I hate these. Look at the size of this. Radial, geodesic, radial, no, geodesic tells you that then this guy here, so dt over a of t is equal to d chi, basically. And then you can integrate, and then you can relate here the radius in hyperspherical coordinates to basically an integral over the scale factor, which you can also turn into an integral over redshift and the expansion rate. This is another exercise that I'll leave for you later. But basically, this is a more useful expression because the sky here can be computed directly from the expansion rate that you can have, for instance, from cosmography or something like this. So this is one of the first ways in which we measure angular distance, which is, again, importantly, has this 1 over 1 plus z factor here, okay? Now, we have other ways of measuring distance. We can, instead of assuming that we know the size of an object, we can assume that we know the properties of an object so that we know its luminosity. So suppose we do know the luminosity of an object. So this object could be, for instance, a Cepheid or RR Lyrae star or even a supernova, if we knew the absolute luminosity of supernova, which we don't, by the way. But for some objects, suppose you know the luminosity, then by knowing that the flux is decaying like 1 over the distance square, we can define that distance in terms of the luminosity by inverting this. So define dl as L over 4 pi f. You turn this around, and then you take the square root, and that's the distance that you have, okay? Now, this is a bit more involved, but in Friedmann-Haber-Walker, the photons from this light source here, they suffer two non-trivial effects. So first, the energy, because of the redshift, basically, falls like 1 plus z, or 1 over a here. Now, the frequency of the photons that arrive to you, which is also related to the luminosity. Luminosity is not only the energy of the photons, but also how many photons you are getting here compared to the photons that are leaving from your source. That also is redshifted by a factor of 1 over a. So you have an overall factor of 1 over a square in your flux here, okay? So both the energy and the, let's say, the flux of photons for any given energy is also affected by a factor of 1 over a here, okay? So that means that your flux here now has a factor of a of the emission divided by a of observation squared, okay? So means that now if we look at this expression, that means that your luminosity distance now is r over a of emission. Now a of emission is just what we call 1 over 1 plus z of the galaxy that emitted that light. So your radius is now 1 plus z times r, okay? So again, using this here for just an exercise for you to do. I mean, just so that you get reminded of this, because this is for luminosity distance, this is not a problem, but for angular distance, this is kind of confusing. Okay. So let's assume that we have two cases here. One of them is that the scale factor goes like t to the 2/3. And that is exactly what you get for a matter-dominated universe. You guys, everybody remember this? Matter domination, how you get a t of 2/3. If you don't remember this, go back to the equation of state of matter, which is 0. Solve the Friedmann equation, and you get that the scale factor goes like t to the 2/3. If you don't remember this, do the exercise. You can also assume that the scale factor goes like t squared. Now, t squared is like some weird fluid here, but it doesn't matter too much. It's just an example. But let's just focus here on this case here, for instance, okay? So this is z. So time is going backwards this way. Of course, the universe is becoming smaller that way, okay? So let's focus here on these two plots here. Okay, so let's first look at luminosity distance, which is simpler. And it's increasing as you go to higher redshift. Remember, chi is increasing, of course. The Comoving distance to an object which is farther and farther away is always going to increase, of course. As you integrate this guy here, let's integrate out, it increases and increases and increases, and this is becoming larger here. Now, the angular diameter distance, on the other hand, it has this funny behavior here, okay? So ignore the k negative and positive cases. Even think just about the k equals to 0 case here, okay? Look at what's happening here. The angular diameter distance grows, reaches a maximum, and then starts to get smaller. Now, why that is? Why is that? Everybody remembers how you can interpret this. So this wasn't a useless review after all. Yes?
The angular size becomes smaller, so...
Actually, if the angular distance is becoming larger, it means that the angular size, in some sense, is becoming larger, right?
Okay.
Sorry. So the angular size is becoming larger, and then it's becoming smaller, right? Larger and then smaller. So it goes up as you expect. If you just see Minkowski, right? As you move away, the angular size of something which is given distance, it becomes smaller. But then here it becomes smaller, and then it starts to become larger again, right? Why is this? Come on. The object is what?
The distance is larger.
The distance, which distance you're talking about? This is the distance. This is the plot of the angular distance here. You can have also the we can express the comoving distance. The comoving distance is always getting larger, okay? It's always getting larger. However, the angular diameter distance it grows and then reaches a peak and then it starts to get smaller. No? Okay, so here's a hint. What's happening to the universe as you go to higher redshift? That means as you go back to the past.
Yeah.
No. We are assuming that the expansion is always like t to the 2/3 here, okay? In any case, the universe is only going to be dominated by radiation at a redshift of 5,000. What is happening as we go back in time to the universe?
Yeah, the universe is smaller.
The universe is smaller. However, your object is still the same size, so it occupies a larger piece of the space in terms of comoving coordinates, right? So it's your object, that B that I told you before, is becoming larger. So if you use any object of fixed physical size, okay, as you go back in time, its angular size will get smaller and then it will become larger, meaning that the angular diameter distance will grow, but then it will become smaller, okay? So that's an important information that you need, especially when we talk about things like lensing later on, because this is going to be sometimes a bit counterintuitive, okay? So typically, at around a redshift of around 1, you know, 0.5, 1.5 or so, the angular diameter distance reaches a peak, and then it starts to go down. That's interesting, but it's true. Okay, so here's a problem for you. Calculate for a given case some of these distances here. Okay, I'm going to jump over this because this is a problem for you for later. You can make basically some of these plots here that I've done. Let me talk briefly about cosmography, not too much. You know that you can always try to measure this directly, this comoving radius, by looking at how things are moving away from us. This is basically how we arrive at the Hubble diagram that I'll talk in a second. So this is how you transform an integral over the scale factor to an integral over redshift. Okay, so you make this coordinate change here. Go from dt to dt, dA, dA. So you transform this into an integral over dA over a squared times Hubble parameter. And then you transform this into an integral over redshift. So this is basically an integral of dz over h. Now, when you do that, be careful that you also change the limit of integration. So there is a minus factor that you have to take care there by including it into the limits of the integration there. Okay, so basically, what you can do now is that you can play the game that, okay, so suppose your scale factor is basically using the expression for h in terms of a dot over a. You can expand this in this way. This is what we call cosmography. So h naught is the first term that appears in the Hubble in the expansion in the power law expansion of a. And the second term here is what we call the deceleration parameter q naught here. Okay, and then you have the quadratic terms. So this is how, let's say, people started to play the game of trying to relate the expansion with the distances and relate all these things together. We can invert this. This is all exercise that you probably have done before, but if you haven't, then it's a good time to try this. You can invert time in terms of redshift here by using this expression here and that expression, and substitute back into here and integrate. And what you get is this here. You get basically that your comoving radius is equal to 1 over h0. So 1 over h0 appears everywhere. Every single distance that you calculate in cosmology goes a 1 over h0, or in actual physical units, c, the speed of light, over h0, okay? So this is always there, and all distances that we infer on the basis of things like this will have an uncertainty that is exactly the same as, at least the uncertainty that you get for h0, okay? And then you have the initial term is just the z, okay? So z is, so the distance, the comoving distance is proportional to z initially, and then you get a quadratic component here that includes the deceleration parameter. And of course, I'm doing this for k is equal to 0. You're welcome to try this for k different than 0, what you'll find is that it's only coming at higher order terms. The z is still there here, okay? In terms of the flux that you measure from an object with a known luminosity, this is what you get then. If you remember that dl is related to this comoving distance in the way that you remember. So this is one of dl square. So you put dl square here, you get this term here to first approximation. Okay. Then this tells you that the flux should go like 1 over z squared, but then there's a factor of z that goes in there. Okay, so before we go into the Hubble law itself, this is something else that we need to review here. What astronomers measure is not flux. They never measure flux in an absolute sense, or very seldomly they do this. They use a logarithmic scale to measure flux. These are called magnitudes. So this is how we express these things in cosmology typically. And you're going to see here when people talk about supernovas and so on. So it's a good thing that I try to revise this thing now. So basically, this is how astronomers define, in a practical way, flux or brightness, if you want, of two objects. Suppose you have two objects of brightness M1 and M2. So they have fluxes F1 and F2, okay? So if you take the log 10 of the flux and you multiply by a factor of 2.5, don't kill me, this is history, always been done this way. It's related to the ways in which humans perceive sound and light and so on, okay? It's a completely arbitrary definition, but that it is. So it's minus 2.5 log of the difference in fluxes, and there's a minus here. So this is how people define relative magnitudes. So if you have two objects, say two stars in the sky, okay? The two fluxes of these two stars translate into two magnitudes. So astronomers always talk about magnitudes of objects, okay? So this is what they do. And how do they do this in practice? They have a standard, and they measure things relative to that standard. This is like the decibel level of sounds, for instance, okay? So the object that people have used for a long time was a very stable, very bright star called Vega. More recently, they finally gave away that Vega. It's like giving up the meter in Paris. You now define it in terms of some absolute physical property of, some sort of state of an atom somewhere. And astronomers have now defined some absolute magnitudes relative to some physical parameters, but let's say for a long time this was the standard. So the apparent magnitude of an object is the flux of the object divided by flux Vega of the Vega star and the log 10 there. Okay, so let's just review here some magnitudes, okay? Remember, because of the minus sign here is the other way around. High magnitude means very faint, and negative magnitude means very bright objects. So here are some apparent magnitudes of objects that you may know. Okay, if you look at the sun, that's an apparent magnitude of minus 27. So it has like 27 divided by 2.5 order of magnitude more bright than the Vega star. Of course, nobody looks at the sky, at the sun itself, but the full moon is still very bright. Venus is 5 magnitudes brighter than Vega. Vega itself, of course, is approximately the same magnitude as Saturn, so it's a bright star, as you know. Now, limit of the human eye is a magnitude of 6. Neptune is 8. Pluto is 14. A galaxy, a typical galaxy, what we call an L-star galaxy at redshift 1, is about 20. The visible light limit of an 8-meter telescope is about 27. You cannot see anything fainter than 27. And the limit for the Hubble Space Telescope, which has basically never been reached because you would need to observe for, maybe has been reached for the Hubble Deep Field, but it's 32. For most of the stuff that we do in cosmology, we rarely go beyond a magnitude of around 23, 24, 25 these days, okay? So we go to galaxies at redshift 1, 2, 3, quasars at redshift 4, something like this, rarely. Okay? Just so that you have an idea here. Okay? All right, so so these are relative magnitudes relative to some standard, but what about the absolute flux, the absolute luminosity of an object? Well, then what astronomers have done is that they again created a certain standard. So the standard distance to an object, such that we call its brightness at a given distance, we call this absolute magnitude. This distance is called is 10 parsecs. 10, okay, 1 parsec is 3.26 light years. And then they define an absolute magnitude of this sort here, okay? So the absolute magnitude here is related to the relative magnitude by something which is called the distance modulus here. So if you divide the flux of that object, of an object, by the flux that that same object would have at a distance of 10 parsecs from us, so that means 32.6 light years, then this thing here is basically, you can write this in terms of the luminosity distance to that object, okay? You see that this, you can always write this in terms of the luminosity distance, of course, okay, right? Divided by 10 megaparsec, 10 parsecs. So this is called the modulus of distance. If anybody is going to talk to you about supernovas and what they mean for cosmology later on, this is what you're going to be seeing. People manage supernovas in terms of this distance modulus here. Okay, so again, distance modulus is related to luminosity distance, which is related to measurements of distance that make some sort of a statement about the intrinsic properties of some light source. So typically what we use are standard stars like Cepheids or supernovas, or more recently other kinds of objects which we can discuss later, okay? So if the absolute magnitude of an object is known, and we measure the relative magnitude, we can infer the distance modulus and the luminosity distance, okay? Put this in your head, not yet in your hand. This is one of the ways in which we can measure distances. This is basically what Hubble did based on the idea of Henrietta Leavitt of using the Cepheids as standard stars. We know the absolute magnitude, we measure the relative magnitude, we infer what this mu is. By inferring what this mu is, then we can calculate what this distance is. That is the idea, okay? So I wanted to say this before we went on to give the Hubble diagram, because this is the way that you measure it, and this is also the way that you measure things in supernovas, okay? You're certainly going to see plots of the distance modulus of supernovas here, so here it is for you, so that you can remember that it's related to this luminosity distance, which is what we calculated before, okay? Okay, now, what has Hubble done here? So, using that absolute magnitude, relative magnitude difference that allows you to infer the distance modulus and luminosity distance, he's done this. We are in time here, okay, yeah. So I'm just finishing here, okay? What? Huh? We are 15 minutes late, yes, I know. I'm going to at least finish here. So this is the Hubble parameter here. So this is distance here. And, sorry, this is distance here. And this is velocity here. It's in kilometers per second here. And this is famous Hubble plot that gave rise to the Hubble metric law. And this is basically how they arrived at this. Now, of course, everybody knows the story. There was a problem with the calibration of the distances in Hubble's data. And they arrived at an expansion rate of 500 kilometers per second because of this wrong factor, okay? Now people have corrected this in many ways, and here are some more modern plots of this for distance and velocity here. This is the scatter between of a linear Hubble law here. This was from 2001, but we have more recent plots here. So here is the original let's say, region where Hubble could make his Hubble plot. And now we know that this is much more, you can extend this to much larger distances. Still, it's valid that you don't need the deceleration parameter. That's still very much in the linear regime here, okay? So basically, this is what we get today. If we use these numbers here, if you make these so-called local measurements of the Hubble parameter here, you get around 73.45, There was a paper from a few weeks ago where they measure 73.53, I think, but it's basically the same. It doesn't change a lot. Now, I'm going to tell you more about the Hubble parameter and the dark matter and dark energy tomorrow, very quickly, because I'm going extremely slow, and I should have. I hadn't told you anything about dark matter and dark energy, which were my next topics. But I'm going to tell you more about this tomorrow, okay? And more about the Hubble parameter tomorrow also, and I'll also start the large-scale structure discussion tomorrow. Okay, so I'll stop here. All right, okay, cool. Oops.
So since it's 10 minutes to 11, I think we can start the next lecture 10 minutes late, if Meredith is
We don't
okay.
have a coffee break, nothing?
Yes, we have a coffee break
Yes.
now. So here on the upstairs.
Okay.
And we can start 11:10 instead of 11.
Okay.
Okay.
Sorry about that, Matt.
No, sorry, I was just...